If we consider a differential equation like the one here, we notice that the right-hand side here has a mix of x's, which are the independent variable, and y's, which are the dependent variable. So this equation here cannot just be integrated with respect to x. Let me just show how that would look. If we tried to integrate x minus 5 over y squared dx, this is a big red flag because we don't know what y squared, or particularly y equals. If we did, remember what we're looking for. We're looking for y equals as our final solution. So if we knew what it was, we wouldn't be doing the work we're about to do. So what we have here is a new complication. And this is the start of our study of, I would say, real or the more challenging differential equations. We want to go from this differential equation down to y equals something with x's in it, in this case here. How are we going to accomplish that? Well, this is going to be our first technique for solving differential equations. And what we're going to note is that the right-hand side of our equation here is the product. We have x's and products quotients are equivalent. We're dividing by y squared. And what that lets us do is separate the variables. So this might seem a little counterintuitive, but if you go and look at the technical integral definitions, you'll see that this actually does work out in practice. What we're going to do is literally separate the variables by bringing the y squared to the other side and bring the dx to the opposite side where it started. What that's going to give us is y squared dy is going to equal x minus 5 dx. And you can think of this as differentials or tiny increments of y and x. The key thing, though, is that we can integrate now, and we no longer have this mismatch of x integrals with y values. Now it's a y integral with y values and an x integral with only x values. So the process here, if possible, is to separate and integrate. 2 steps there. Once we've done that and you've verified that, yes, the integral here makes sense, there's no x's, and this integral here with dx has no y's, then you can go to town and use all the classic integration skills at your disposal. Here, y is our variable. It's a power of y, so we add 1 to the power, divide by the new power. On this side, we can integrate term by term, and we get x squared minus 5x. Now, there is the issue of each integral having a plus c, and you're welcome to, if you wanted, to put like a c1 plus here and a plus c2 here. But at the end of the day, remember the goal. We're looking for y equals. So everything is going to get put to the other side. So what we do in practice here is we don't put 2 constants. We just put 1 big constant on the right-hand side, which would be the total lumping together of any constants from the first integral and constants from the second integral. Another way to say that is these 2 integrals differ by a constant, and it doesn't matter which side we put it on. We're going to put it on the right because that's where we want it to end up anyway. So with that in mind, now we're actually done the hard part in the sense that we started with an equation with derivatives, dy dx. By integrating now, there are no derivatives left, so it's simply a regular or algebraic equation with y's and x's. We can now solve for y by manipulating the equation. Bring the 3 up, and that'll give us 15x's and 3c's. Then at the end of the day, y will be the cube root, I'll write it as a power, of this entire expression here to the power of 1/3. And that becomes our process for solving equations where we can, through cross multiplication, separate the variables. Notice that there is a c in here, so this is a family of solutions, or the general solution. And the c doesn't show up in quite the plus c way that we saw in some earlier examples. It can show up in more interesting ways here. But that would be a perfectly valid general solution to this differential equation. That being said, it behooves us, seeing as we saw this earlier, to verify the solution. In other words, check that it's actually correct. Well, we just said that we had 3x squared over 2 minus 15x plus 3c to the power of 1/3 is our solution. What we can do is go to our differential equation and try to sub this in. If it is the correct solution, it'll satisfy it, and the left-hand side will equal the right-hand side. The left-hand side is the derivative with respect to x of that entire thing. So, just to warn you, in this class, there's quite a bit of algebra, quite a bit of long equations to work with. So this is a good acclimatization. The derivative with respect to x of all this is we bring the third power out front. We have the same interior. And then we have negative 2/3 as our exponent. And then we multiply through by the derivative of the inside. That would be 3x, the x squared over 2, the 2's cancel, minus 15. Now, it's not entirely obvious how that relates back to the original. So let's take a look at the right-hand side separately, which is the x minus 5 over y squared. Well, x minus 5 is what it is. The y squared shows up here as 3x squared over 2 minus 15x plus 3c to the 2/3 if it's squared, and we had 1/3. And if we take a careful look, this term here is exactly equal to that term there. And if we multiply this 1/3 in, we end up with x minus 5, divided by all that same expression to the 2/3. So in fact, these two sides, the left-hand side coming from the derivative and the right-hand side coming from the algebraic expressions here, those are equal. And so we have the correct solution. Y equals our 3x squared over 2 minus 15x plus 3c is the correct solution.